Part 2 is a derivative of the first part of the question. So this integral is going to be using the first part of the question, 1 over n x squared sine nx plus 2 over n squared x cosine nx minus 2 over n cubed sine nx, and omitting the c, but I go for a lower limit of pi and upper limit of 2 pi. Let's substitute 2 pi in first. So it is going to be 1 over n of 2 pi square sine 2n pi plus 2 over n square of 2 pi cosine 2n pi minus 2 over n cubed sine 2n pi. And this minus away, substituting pi in, minus away 1 over n of pi square sine n pi plus 2 over n square of pi cosine n pi minus 2 over n cubed sine of n pi. And if we were to do the analysis for sine of 2n pi and sine of n pi, let's try to revisit our sine curve. Sine curve is going to be something that is like this. According to what we have learned in the secondary school, one period is going to be this, fluctuating between -1 and 1. So if you are looking at multiples of pi, integer multiples of pi, so we are looking at this value, 0, 1 time of pi, 0 time of pi, 1 time of pi. This is going to be 2 times of pi. If I were to continue for the next period, here I have a 3 times of pi, and here is 4 times of pi. So I know as long as it is an integer multiples of pi, sine of the angle is always going to be 0, which means that this is going to be 0, 0, and here 0, and this is also going to be 0. So we can simplify this. This is 0, so I'm going to be left with 4 pi over n square cosine 2n pi. And we're going to be left with this. So minus away 2 pi over n square cosine of n pi. Let me factorize out pi over n square, which means that I'm going to be left with 4 cosine 2n pi minus away 2 cosine of n pi. And now let's do another round of analysis for cosine of an angle that is multiples of pi again. So if I were to revisit the cosine graph, let me sketch it here. For one period, it is going to be like this, fluctuating once again between -1 and 1. And we're trying to analyze integer multiples of pi. So we are analyzing this, which is pi. It's going to give me a -1. And here, when it is at 2 pi, it is going to give me positive 1. And if I were to draw another period, 3 pi is going to give me -1, and 4 pi is going to give me positive 1. So if I were to look at this, what we have here is an even number of pi, even integer number of pi. So from what we see here, even multiples of pi, 2 pi, 4 pi, they will consistently give me a 1. So this will be pi over n square of 4 times 1 minus 2 times of cosine n pi. That means I have an integer multiple of pi. All these are integer multiples of pi, which means that for this particular value here, it is always going to be fluctuating between -1 and 1, which we'll consider in a short while. So I'm going to leave this as cosine n pi. So what we have now, the simplified version will be this of 4 minus 2 cosine n pi. And now we got to try to consider whether n is even or odd. So let me do it here. If n is even, so if I were to let n be equal to, let's say 2k, where k, I will let it be positive integer, since n must be also a positive integer. So if n happen to be even, that means we are looking at this and this. So this portion here is going to be always consistently giving us a positive 1, which means that the integration from pi to 2 pi of x squared cosine nx will be pi over n square of 4 minus 2, like what we discussed, this is going to give me 1. So this is going to be 2 times of pi over n square, which means that a, according to the question, will be this number here, a is 2. And if n is odd, so for example, it is 2k plus 1, where k is also a positive integer. That means if we are considering n as odd, we are looking at this, and so on. And for odd numbers, odd multiples of pi, the output of cosine of the angle is always going to be negative 1. So the integration of from pi to 2 pi of x squared cosine nx dx. This will be pi over n squared of 4 minus 2 times of minus 1, which is 6 of pi over n squared. So the a value, which is this value, is 6.